Assalamualaikum and salam sejahtera to Dr. Mohamad Nazim bin Jambli. Today, my group and I will be presenting our computer architecture group project. First, our group members, we have Mohamad Syakir Jubair, which is me, 105080, Mohamad Shafifi, 105281, Ka Hou, 103617, Mohamad Fadzilah, 105001, and lastly, Mohamad Arif Faridzuan, 107626. First is question 1, which is my part, basic operation of CPU architecture simulation. Okay, for 1.1 is the simulated CPU architecture definition. Okay, first, program counter. Program counter is used to keep track of which instruction comes next in our simulation. It is a simple number that starts at 0 and increases by 1 after each instruction. Next is instruction register. The instruction register holds the current instruction that the CPU is working on. Next is general purpose register. There are four general purpose register in our CPU, which is R0, R1, R2, and R3. These are used to temporarily store number and results. In our simulations, they are stored in dictionary, kind of like a small table, which each register has its own value. Number 4 is arithmetic logic unit, ALU for short. ALU is used to do calculation like add and sub. In our simulation, the ALU is just a normal addition or subtraction in the code. And lastly, memory. The CPU uses memory to store both instruction and data. And in our simulation, the memory is a list with 64 slots, and each one holding a number or an instruction. Okay, next is small instruction design. Okay, first we have the first mnemonic, which is load. It has an operation code of 0001, and it is used to load value from memory address to register. Next, which is store, with the operation code of 0010, it is used to store value from register into memory address. Next is add, with the operation code of 0011, which add value into register, and it is stored in the first register. Next is sub, with the operation code of 0100. It subtract second register from first, and then it is stored in the first register. Next is JMP, with the operation code of 0101. It jumps to instruction at given address. And lastly, we have halt, with the operation code of 0110. It is just to stop the program execution. Here we have the operand code. We have the register R0, which has the binary of 00, register 1, 01, register 2, 10, register 3, 11. Below is the example address. We have 4, and it has the binary, which has 6 bits, 000100. And another example is 20. It has the binary 6 bit of 010100. We use 6-bit binary numbers since our memory has 64 slots, which is 2 to the power of 6, which is equals to 64. Lastly, for my part, is the CPU simulation program. We use the Python program to run the simulation. Okay, the simulation will perform the following steps. The first is it loads the value from 5 from memory address into memory address 20 into register R0. Next, it load the value 10 from memory address 21 into register R1. Third, add the values back into R0 and R1 and store the result back into R0. Number 4, store the result from R0 into the memory address 10. And lastly, it will halt the program. Okay, that is all for my part. Thank you.
Hello, my name is Mohamad Shafifi Samsul and my matrix number is 10581. And I will be presenting on 1.4 executing program output. Here, we did a 5-cycle run on the CPU simulation program, and this is the output on the CPU simulation program. Here, I'll be expanding on the table. So first, on the first cycle, the instruction is load R0 and 20 is fetch. The CPU loads the value 5 from memory address 20 into register 0. So as you can see, the register now is R0 equals to 5, while the address is 0. On the second cycle, the instruction loads R1 21 is executed. The CPU loads the value 10 from memory address 21 into register 1. Register now is R0 equals to 5 and R1 is 10, while the address is 0. On the third cycle, the instruction adds R0 and R1 is executed. The CPU adds the value in R0 and R1 into 5 plus 10 equals to 15 and stores the result back into R0. Register now, R0 equals to 15 and R1 is 10, while the address is 0. On the fourth cycle, the instruction store R0 and 10 is executed. The value in R0, which is 15, is stored into memory address 10. So, on the memory, 10 now contains 15, which is the correct result. On the fifth cycle, the instruction halt is executed. The program stops, and all final value in registers and memory remains unchanged. That is all from me. Thank you.
Good day, Doctor. I am Ka Hou 103617, and I will continue the presentation from 2.1, Principles and Performance of Cache Memory. So, the first thing, cache memory is a high-speed memory that's closer to the CPU compared to the others such as main memory RAM. As such, it has reduced access time. The cache memory is used to store frequently accessed data or instructions and are structured as level 1, 2, or 3, or formerly known as hierarchical. Now, we look at the comparisons between the three levels of cache. For the first level, or level 1, there are only 1 to 2 CPU cycles containing sizes from 16 kilobytes to 12 kilobytes. The locations are stored at each core, and the purpose is immediate ops. For level 2, there are more CPU cycles from 4 to 12, increasing the size as well to 256 kilobytes to 1 megabyte. It can be stored per core or it could be shared between them. And its purpose is to function as a buffer for level 3 or also known as RAM. For level 3, we have more than 20 cycles usually, with size from 2 megabytes ranging up to 64 megabytes. It's shared between all cores storage-wise, and well, as mentioned just now, its purpose is to share its storage. Now that the differences between the three levels of cache are clear, we will look at the mapping strategies. There are three types of strategies that we have looked into in this project. The first one is direct map, where one block is mapped to one line. It is very fast, but it is prone to conflict. For the second strategy, we have fully associative. It is the slowest or the most complex, but it is the most flexible in exchange. It aligns any block to any line. For the last strategy, it is set associative. It aligns a block to a set, then the set to any line. It is the most balanced approach out of the three strategies here. Alright, the next part is replacement policies. We have least recently used, which evicts the least recently used. It has a high hit rate and provides overhead in tracking. The second one is first in, first out, where it evicts the oldest block. It is simple, but it may evict useful data. The third one is random replacement. It evicts data randomly, the most easiest to implement, but the results are unpredictable. The key takeaways is that cache memory reduces memory latency, and level 1 to level 3 trade-off speed for capacity. For strategy, direct map is the fastest but least flexible. Associative mapping improves the performance at the cost of complexity. And as such, we move to the last one, replacement policy methods. We will usually use least recently used over first in, first out, over random. That's all from me. Thank you.
Hello, my name is Fadzilah by Marikan. My registration number is 105001. Today I will present cache simulation for our computer architecture group project. For the first part, we use matrix multiplication. The simulator we use is the custom built in Python or online Python. You can use it in your locally Python program used is 32 by 32 matrix multiplication, and the purpose for this catcher simulation is to study catcher hit or miss performance, test how the catcher sizes, the block sizes and the replacement policies affect results. And for the mapping, we chose direct map. This is the coding for the matrix multiplication. This is the catcher results and settings. For the catcher sizes, we have 4 kilobyte, 16 kilobyte, 64 kilobyte. Block sizes, we have 16 byte, 64 byte and 128 byte. For the policies, we have 3 of them also: LRU, least recently used, and then first in, first out, and then random. This is one of the coding snippets that will use this catcher sizes, block sizes and policies, and the results will vary from each of them. Then this is the matrix generation and the matrix multiplication. This is the coding itself. It's more than the original for the first part coding. You can see here this is longer, but you can see that it will increase the size according to the parts here. This is also the codings. And last but not least, the conclusion is observations: bigger catcher equal to better performance, larger block will equal to better liquidity, LRU is better than first in first out, and first in first out is better than random. You can say least recently used LRU is better than random. And then direct map catcher is fast, but it may cause conflicts if there's too much data at the same time. Simulation helps us understand CPU memory behavior is the observation and the conclusion for the catcher simulation. For the results, you can see it from my friend later on when he present the next part. That is all for me. Thank you.
Hello, my name is Mohamad Arif Faridzuan, and I'm going to present catch simulation and the analysis. So first, this slide shows the result from our catch simulation. We ran 3 tests using the different catch and block size configuration. Each test had the same number of total memory access, 98,304, but the hit and miss result varied. As shown in the table, test 1 had a hit rate of 99.74%, while test 2 improved slightly to 99.93%. For test 3, achieved the best result with 99.97% hit rate and the lowest miss rate of just 0.03%. So below this table, we can see 2 graphs here. The first one compares the hit and miss rates for all tests using simple bars. The second graph gives a stacked view of hit and miss rates, which makes it easier to see how little data was missed in each case. This result clearly shows that changing cache configuration has a direct effect on performance. Okay, next is analysis and insights. So based on the data, we can conclude a few key points. First, increasing both cache and block size led to better performance. In particular, test 3, which used 64 KB cache and 128 byte block, gave us the highest hit rate. Second, the use of a direct map cache with FIFO replacement policy worked well, likely because the matrix multiplication task had a predictable access pattern. And overall, this simulation highlights the performance of selecting the right cache configuration, especially for memory-heavy computation. Better cache design can reduce access time and improve the CPU efficiency significantly. And that is all from me. Thank you.